Can you hear me? Can you hear me? Did you say turn my walkie-talkie off? I now call to order the Society's 2,412th meeting in the 149th year since its founding on March 13th, 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Daniel Inocente in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW Science's YouTube channel. We will begin with a few announcements, followed by a reading of the minutes of the 2,411th meeting and the lecture by Jared Kaplan on quantum gravity. We will then turn to this evening's lecture, followed by a question and answer period. When the Q&A session is done, I will present a small thank you gift to our speaker, make a few closing announcements, thank those who make PSW possible, including our crew tonight, and adjourn the meeting to the social hour. First, please join me in thanking, there we go, the sponsors of the 2019-2020 lecture series, the Policy Studies Organization, in cooperation with the American Public University, and a generous sponsor who has asked to remain anonymous. Also, please join me in thanking the sponsor of tonight's lecture, PSW member Mayumi Okada, who is in the audience. Thank you, Mayumi. And please also join me in welcoming our new General Committee member, Cameo Lance, who is joining the GC as Director of Special Projects, upon appointment by President Milstein, that would be me, and unanimous approval of the General Committee. Cameo is Director of Physics Programs at RIA Space Activity. Welcome, Cameo, and thanks in advance for the hard work and many long hours you are now going to devote selflessly to PSW science. I am pleased to announce that the following new members have been elected to the Society. Peter Bishop, a software engineer with Aero Prize, interested in computer science, brain science, microbiology, and philosophy, who learned of PSW science through the Washington Post. Elizabeth Landau, a senior storyteller and public affairs officer with NASA JPL, interested in astronomy and cosmology, who learned of PSW science by, quote, word of mouth, close quote. Michael Salomon, a physicist with the Department of Energy Office of High Energy Physics, interested in astrophysics, cosmology, and quantum gravity, who learned of PSW from a friend who is a member. Jacqueline McQueen, lead biologist at the EPA, recently retired, interested in biology, chemistry, human health, and ecological risk assessment, public health and policy, who learned of PSW through a PSW Science lecture announcement. William Angel, a data analyst with knowledge to practice, interested in data sciences, information visualization, energy technology, and material sciences, and space exploration, quote, alongside everything else, close quote, who comes to PSW through Meetup. Elizabeth Quist, a graduate student in National Security Operations at the Institute of World Politics, interested in technology, astrophysics, bioengineering, and behavioral psychology, who, very interesting, learned of PSW through her interest in the history of the National Geographic Society, which was founded here at the Cosmos Club by a number of PSW members, reputedly in the eponymous National Geographic room upstairs from us. And tonight's speaker, Daniel Inocente, whose background and interests will be clear to you, in part, from tonight's proceedings. Please join me in welcoming them all to membership. All new members can receive a signed reprint of Volume 1 of the PSW Bulletin. If you are a new member and you have not received yours, please see me after the lecture, and I will be happy to give you a copy where you can read the original bylaws and a statement of why the organization was founded, and you can peruse who the original members were and read a number of their interesting presentations at the early meetings. And if you purchased the PSW ribbon, please see Social Media Director Ann McQueen at the ribbon table to pick it up. Recording Secretary James Heelan will now read the minutes of the 2411th meeting and the lecture by Jared Kaplan on quantum gravity, delivered to the Society and guests in this room on September 6th, 2009. James.
Thank you, Larry. Good evening. On September 6, 2019, here in Washington, D.C., President Larry Milstein called the 2411th meeting of the Society to order at 8:05 p.m. He announced the order of business, that the evening's lecture would be live-streamed on the internet, and addressed the annual business of the Society. President Milstein then welcomed new members, and the minutes of the prior meeting were read and approved. President Milstein then introduced the speaker for the evening, Jared Kaplan, Associate Professor of Physics at Johns Hopkins University. His lecture was titled, Why Quantum Gravity is Different. The standard model of particle physics describes three similar forces: electromagnetism, the weak force, and the strong force. Kaplan said gravity has been considered similar to those forces, but in recent decades it has become clear that gravity is so fundamentally different from those other forces as to revolutionize the understanding of space and time. The standard model arose from scientists colliding particles to learn about their constituent parts in short-distance interactions. In 1911, the Rutherford-Geiger-Marsden experiments beamed alpha particles through gold foil to discover atomic nuclei. In 1968, using higher energy, the Stanford Linear Accelerator used deep inelastic scattering to substantiate the existence of quarks. Subsequent collision experiments at even higher energies have revealed the Higgs boson, W and Z bosons, heavy quarks, and mesons. Kaplan said this reductionist approach has illuminated more macroscopic scientific understanding. For example, understanding the forces of attraction and repulsion at work in atoms allowed scientists to deduce the limitations on the number of elements in the universe. Similarly, scientists were able to predict the existence of particles like the Higgs boson prior to their actual discovery. Kaplan said one means of predicting future discoveries is through observing very weak forces at great scale. For example, gravity is billions of times weaker than electromagnetism, yet we know gravity exists because we experience its large-scale effects. That gravitational forces are proportional to energy distinguishes it from the other three forces in the Standard Model. With extremely high energy, gravity will become as consequential as electromagnetism, and at the Planck scale of 10 to the minus 35 meters, gravity will be as significant as the other forces. If scientists were able to observe forces at this scale, Kaplan believes they could deconstruct gravity similar to how scientists have deconstructed particles. Classical gravity is Einstein's theory of general relativity, whereas quantum gravity seeks to describe gravity according to the principles of quantum mechanics. In general relativity, black holes are inescapable and cannot be explored with high energy physics, because adding energy will only make the black hole bigger. Kaplan said, physics is about describing the states of nature and how they change with time, and information is a description of a state. He then said in 1972, Jacob Bekenstein theorized that the information stored in a black hole is associated with its event horizon area, not its volume. If true, then volume, space itself, cannot be fundamental. This means the fundamental theory of physics must have fewer dimensions than previously believed. One proposed solution is holography, the idea that a flat surface can be encoded with all of the information in a volume. At its heart, holography connects gravity and a space called ADS with conformal field theory, which is scale invariant. Addressing the question of how a living in 2 dimensions has 3 dimensions, Kaplan said the extra dimension is the, quote, zooming in and out of the scale invariant field. Kaplan then summed his talk by stating that although reductionism has been successful for discovery of the Standard Model, it apparently cannot be used to explore gravity. He believes holography will lead to a better understanding of quantum gravity, particularly the physics of black holes. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:58 p.m., President Milstein adjourned the meeting to the social hour. Temperature, 22 degrees C. Weather, mostly clear. Attendance in the Powell Auditorium, 161. And viewing through the live stream on the PSW Science YouTube channel, 63. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Are there any corrections or comments on the minutes by a member? So it's all very clear to you, or not clear at all. Hearing no comments or corrections, I will entertain a motion by a member to approve the minutes as read, except you always do that. Some other member. Okay, there's one. Do we have a second? Okay, Bob, you get the second. All members in favor? Aye. All members opposed? The minutes are accepted as read and will be posted to the website in due course. We now turn to tonight's lecture on space architecture for a moon village, designing for space habitation. And it is my pleasure to introduce tonight's speaker, Daniel Inocente. Daniel is a senior architectural designer with the storied architectural firm of Skidmore, Owings, and Merrill. I'll take a side, if you don't know Skidmore, Owings, and Merrill, you should immediately go to Wikipedia and read about it. He's a leader in the Design Science Computation Group and plays a leading role in building partnerships with other organizations, like the partnership we'll hear about tonight between Skidmore, Owings, and Merrill, the European Space Agency, and the Massachusetts Institute of Technology. In addition to his current position with SOM, Daniel has worked with a number of other storied architectural firms, including Gehry Partners and Gehry Technologies. Along the way, he's worked on a variety of large-scale projects in diverse environments, scanning the globe from Abu Dhabi to London to China and the US, and from earthly projects like Frank Gehry's residence to moon bases like the one we'll hear about tonight. And in between, he's worked on the design of very tall buildings like the Zhangtian skyscraper in China. Daniel is committed to the view that research leading to the development of new methods that can be applied in action drives performance improvements, increases efficiency in material and energy use, improves the behavioral responsiveness of designs, and is crucial to improving the practice of architecture. He believes that negotiating the relationships between contemporary urban systems, expressive qualities, and engineered architecture is fundamental to achieving new forms of functionality and elegance that elevates the human experience. He studied architecture at the Southern California Institute of Architecture, focusing his thesis on environmental science and infrastructure design. Please join me in welcoming Daniel to the podium, and hold your questions to the end and the Q&A period. Daniel.
Thank you. Hello, can you hear me? Good. Thank you, Larry, and thank you to Larry's team for putting this together. It really is a privilege to be here with everyone here, and also an honor to speak in front of PSW. Before I jump into talking about moon bases, I just wanted to say that the work that we've been doing is truly interdisciplinary. It's not just me working on all these things that you're about to see today, but it's the culmination of a lot of work that has gone and taken place over the past several months. And I have to thank the leadership at SOM for giving me this opportunity to take on this kind of work, because research really is critical to the way that architecture can impact the world, especially since we all know that the building sector as a whole impacts the world in the most immediate ways. Also, I want to thank the people at ESA, especially the leadership at ESA, for helping me put this together. They've been very instrumental in putting the partnership, and also the leaders at MIT, including Jeffrey Hoffman, who is a teacher and professor at the Department of Aero and Astro, and also Valentina Sumini from the MIT Media Labs, who's been very instrumental in working on this. So, to start off, I wanted to first, for those who are not familiar with architecture as a discipline, talk about what architecture is from the perspective of engineering, but also from the perspective of making and trying to visualize what an architectural idea could be. And if you think about the Brunelleschi's tower in Florence, one of the key paradigms that he innovated with here was his mode of representation, where a structure like this had never been built, and at that time, modes of representation were still very, very crude. And so in order to achieve this, he had to convince a lot of people that he can make it happen. And the only way that he could do that was by building scaled mock-ups where he can demonstrate the ways that this dome structure would work. And so moving forward, we think about La Sagrada Familia, where some of the physical models being used to demonstrate that this could work were actually the characterization of the structure, the hanging chain models that Antoni Gaudi put together. And what you see there is a shift from representation in materials to actually letting the materials demonstrate what the architectural form and structure would be. And more recently, if we think about the Guggenheim in Bilbao, we see that, of course, there's a need to express some artistic manifestation, but there's also a new use of digital technologies to be able to achieve this kind of geometry. And it's Gary who pioneered the use of CATIA software being used in the aerospace industry well before it was used in the building industry. And today, projects like the airport in Beijing by Zaha Hadid, we see that there's a really big advance in how technology is being used to represent ideas of structural qualities and form, but also to discretize both the enclosure and the structure as one. So what we see here is we see an evolution of digital technologies and modes of representation to affect architectural methodology. At SOM, we work on all kinds of projects, everything from small scale, including additive manufacturing projects, to large scale skyscrapers. And what you see here is you see every building looks different, and that's because every building has to function different and has to respond to a very different environment. And so we calibrate our designs and inform them by looking at the environment, looking at urban systems, looking at material qualities, and also looking at the client's needs. But this small depiction of the project you see here is only a small fraction of the work that SOM has done. And so we go from tall structures. Some of these buildings go up as high as 828 meters, like the Burj Khalifa. And some of these buildings, which have big ideas on how to use energy, like the Pertamina Tower. A project that was very fortunate to work on, the Guyong World Trade Center. This one takes urban integration to the next level, where we look at a tower not just in isolation, but we also look at the tower and how it integrates into a much larger urban system. And then we also have much smaller projects taking place at SOM. These are research projects where we're working in collaboration with institutions like the Department of Energy or the US Army Corps to look at new ways of manufacturing. In the top project, the AMI project, that's a project where they're using polymers to 3D print entire structures. Then on the bottom, we're using gantry systems together with additive manufacturing to look at how we can build using cement. And a lot of the things that we do for both small and large have to deal directly with digital technologies. And what you see here is a representation of a digital model on the left, the quantitative data right next to it, and then also the scripting techniques that we use to build these very densely populated models. And all this allows us to think about architecture as form, but also architecture as engineering. So now I want to move on to talking about this research with the moon base. It's, like I said before, it's truly an interdisciplinary project. And what I want to instill is that these kinds of ideas can only take place through direct collaboration. But because ESA is really far from us, obviously, we do have a methodology for how we do the research. And so it's treated more like a project and less like a research project. And so the goal is to take all of the knowledge and the expertise that we have built to construct cities around the world and to pass that on from an architectural perspective towards building outside of Earth.
We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept.
That's one small step for man,
One we are unwilling to postpone.
one giant leap for mankind. Three,
So to start off, I want to first demonstrate the vision. So the architecture and vision of a long-term human settlement on the moon requires a holistic approach to planning, emplacing, constructing, and expanding an evolving lunar ecosystem. An open architecture will depend on the efforts supported by multiple nations and partners, combining their expertise and capabilities toward the common goal of expanding human presence in space for both exploration and development. The vision begins with a singular architecture, which is designed to enable surface exploration and resource utilization operations, leading to a diversity of activities that will evolve and transform an architectural paradigm for living in the lunar environment. And what you see here is that vision. And so the partnership, like I said before, is between MIT, SOM, and ESA. But what you don't know is the kind of capabilities that we're bringing to the table. And so at SOM, primarily in New York, we have the digital design team, we have structural engineers, and the architects. And together with ESA's knowledge of policy, strategic development, and also partnerships, but more than that, with their technical capabilities from STech, we're looking at space technology and science, additive manufacturing, life support systems, also looking at mission design scenarios, and of course, human systems. Because in order to design a habitat for humans, you need to first think about the human limitations and human factors. And MIT brings with them experience in spaceflight, where Jeffrey Hoffman, who's actually been in space to the ISS and has serviced the Hubble Space Telescope, helps influence the project's direction and how we start to articulate some of the criteria. So here's the team. On the left, the team from SOM. In the middle, the team from ESA. And on the right, the team from MIT. And you can see that there's a lot of young faces here, because we like to integrate a lot of the research topics with our younger members in the team. And so to talk about extreme environments, we already have habitats in extreme environments. If you think about McMurdo Station, where you have more than 100 buildings sitting in the Antarctic, there's a lot of planning that goes into this. There's also a lot of infrastructure and a lot of resources that need to be shipped. So learning how to live in an extreme environment is already taking place on Earth, and this is something that we should keep in mind. But also, we have to think about urban development at large scales, because once we see the promise of how to exploit or how to develop the lunar surface and its environment, we're going to see that there's going to be a lot of interest and a lot of expansion. And so planning strategically, thinking about the far future, will have an impact on that. And we can see that places like New York, Manhattan, where you have huge, very dense populations, but also because of the geographic limitations, the only way to build is to build up. And then thinking about space settlement, we already have a space settlement, permanent space settlement, which is the ISS, which has been continuously operated since 2000. So we already understand what it means to live in space. With a small population, of course, never bigger than 6, but also a very small habitable area or volume in this scenario, because now we're thinking about volume and less about floor area. And so if you think about the difference between pressurized versus habitable, this is a big distinct factor where you want to really design around habitable volume, since that's the only thing that you're going to be using. In this case, we have 388 cubic meters of volume. And now, to think about the moon as a site, we see that there's a lot to contend with. The moon comes with extreme environments, but it also has a lot of opportunity. It's considered the 8th continent, roughly the size of Africa. And because of that, there's a lot of interest, but also because of its available resources. And what we've done is we've started to study the moon together with our partners at ESA, and to look at what are the key necessary criteria for evaluating a site for optimal development. And one of those things is the terrain. So we have 2 distinct types of terrain. We have the Maria, then we have the highlands. And we know that in the South and the North Pole, we have primarily highlands. But the highlands also offer an opportunity to capture sunlight because of the altitude. And because of the obliquity of the moon, which is something like 1.5 degrees, there's areas where you have near continuous sunlight, which allows us to think about energy collection. And that's something that we've been targeting very closely because in some areas you have as much as 86% of near continuous daylight. And that means that by lifting your structures just a little bit off the terrain, you can actually take advantage of that energy. But also, you can take advantage of direct-to-earth communications so that you can teleoperate equipment and robotics on the moon. And the most important one, which we see as a medium for energy, is water, but also as a medium for life support, for oxygen, to have breathable air. And we know that there's cold traps on the South Pole, and this hasn't been completely accurately quantified, but we know that there's a lot of it. And some of the mapping done from previous missions has demonstrated that. And so we've studied that together with ESA to help identify small water ice deposits, not large ones, because those would be really far to reach and hard to reach, but smaller water ice deposits. And so we've targeted an area around Shackleton Crater on the west side, looking at the location and character with small water ice deposits, which you see here in red. And what's unique about this area is that it also meets the highest points on the moon, which make, again, increase the amount of energy that you can collect, but also supply us with direct Earth line of sight. And lastly, of course, we have lunar resources, which are inside the regolith. And so if you think about the opportunities that the regolith provide, being primarily silicate and oxide minerals, we can take the regolith, we can take the metals, we can produce tension structures, we can produce materials for life support, we can produce composite structures to help shield from radiation, but also we can learn how to operate and how to build on the moon. And so in some areas, in the Merrill areas, we've noticed that research has indicated that the thickness of the regolith is 4 to 5 meters thick, where in the high regions, it can reach as much as 10 to 15 meters thick. And so it's something that we have to study because if you're going to build a solid foundation, you're not going to hit bedrock. You're going to have to find ways to sinter the regolith to build a solid foundation. And the way that we've done this is by taking information from the LRO mission and creating topographic models, 3D models, three-dimensional models that we then slice up and we start to evaluate for levelness. So the less change in topography, the better, because we know that we have certain landing capabilities that can, land with a certain precision. And if you can identify an area on that part of the moon where you can land equipment, but you can also ensure that there's enough mobility, then you have a good site. And so we've done this for various different sites, and that's how we came up with that site. So the next thing is also fuel, something that we understand is really a big constraint, because in order to get out of the deep gravity well of the Earth, you have to reach a certain delta V, which is 6.1 kilometers per second. And so that constitutes a lot of the vehicle mass that you have to consider. And we understand that this is not something that we're going to completely work through, since we're not in the business of transportation systems, but it's something that we build into our design thinking so that we understand the mass penalty that our structures have to incorporate. And some of the vehicles that we've been looking at more recently include the Falcon Heavy. The Falcon Heavy is what we see as a low-volume, high-mass vehicle. And then we also looked at the New Glenn, which is more of a high-volume, low-mass vehicle. And then hopefully, when the BFR comes online, we can start to think about larger architectural types. And if you look at the numbers, for example, the Falcon Heavy can take 63 tons to LEO, where the New Glenn can take 45 tons. And of course, the BFR could take a lot more. And what we've done is we've tried to optimize our mass in our structures and our designs to meet the payloads for any one of these vehicles. Here's a depiction of what the fairing looks like. So when we're designing, we're actually thinking about the volumetric constraints of the fairing for the SpaceX vehicle. In this case, we have about 145 cubic meters of dynamic volume, where in the case of the Blue Origin vehicle, we have roughly 400 cubic meters of dynamic volume. And one of the things that we've tried to incorporate is also the fact that the fairings also taper. And because they taper, our designs are also trying to maximize the volume, and so we start to think about how we can fit structures that taper into that form. And we looked at various classes of structures. So we understand that there's a class 1 structure, something similar to what you see on the ISS, where you have everything pre-integrated. It's a rigid shell structure. There's also modular systems that you can put together or assemble in space. And then you have future structures, which are more in situ. And those are the ones that we'll touch on briefly at the end. And these are the two paradigms that we're trying to hybridize. So we've looked closely at the ISS capsules. And then we've also looked at more recent technologies, like the inflatable shell technology that's being developed by NASA and also other commercial partners like Bigelow. But we're starting to put together ideas that can hybridize these structures, because for surface applications, you can't entirely rely on an inflatable structure. There needs to be some kind of grounding, something rigid to support the multiple floors and also all of the systems inside. And this is what our design looks like. This is in-flight preparation. And so you can imagine that the vehicle on the right, that's the habitat in its compact form, and then on the left, on the far back end, that's in its inflated form. And to go back into how we design these systems, first we think about the kinds of operations that would take place. It's like designing a house. You have to think about the activities that would take place, like how much space do you need for berthing, how much space do you need for EVAs, how much space do you need for working, for all the kinds of activities that we imagine would take place. And in the first scenario, for the first crew, we understand that there's going to be a lot of heavy work, which means the emplacement of a first habitat also means the preparation work that needs to take place in order to bring additional missions and additional astronauts. So in this case, we prefer a lot of EVA space, and this is more or less a schedule of how we imagine the day of an astronaut's life taking place. And for a second crew, we started to appropriate more research time, more research space, to think about the kinds of operations that they would be doing, like science experiments or operating vehicles from a distance. But also looking at the dimensional constraints, because dimensional constraints on the ISS or on Earth are very different from what they would be on the Moon. In this case, you're looking at diagrams which would be for the ISS, for deep space. And we can only study these to a certain extent because we need to start to come up with our own dimensional constraints. And here you see that for space applications, living, the human body occupies something like 2.7 cubic meters of space. For hygiene, it's about 2.3 cubic meters of space. And for working, it's about 4.3 cubic meters of space. And so when you compare that to other spacecraft, like the G200, which is an airline spacecraft, you're looking at a pressurized volume of 3.1 cubic meters or a free volume of about 2.5 cubic meters. And if you look at the Orion spacecraft, you have a pressurized volume of about 2.5, but for every individual, you have 1.1. That's really constraining. So you wouldn't use that kind of criteria for volume for a habitat on the Moon. The other considerations that we took a look at were also the way that you configure the spaces, the kinds of interfaces that you would develop in place inside, the kinds of translation techniques. So if you ladder stairs, also the restraints for mobility, and also windows, a very important part of the design, and lighting, of course, for maintaining circadian rhythms. So what you see here is a depiction of the habitat system. It's kind of, I understand it's kind of hard to see, but the shell is ghosted, so you can see the inside of the structure. And we've designed it of course, in the vertical configuration, most of the translation or circulation takes place through the center, freeing up the periphery. And so once in its inflated state, we drop down these deployable beams, which then you can place panels on top to support the floor structure, and then push all of the rack systems or the ISPR systems to the perimeter for all the payloads that you would need. And so the way that we develop these models, because they have to be parametrically driven, otherwise what you end up with is a design model that gets criticized, and then there's something not working well, so you have to take it apart and start all over again. In this case, we're using PLM platforms, where you can look at the life cycle of a model, you can look at the engineering, you can look at the mechanical systems, you can look at the structural systems, and we divide each one into its own discipline so that we can then work on each one system in isolation, get information from the team, get information from the engineers, from our consultants at ESA, and then integrate that knowledge and information back into the model. And what you see here is ghosting of the floor system. This is in the schematic stage, a ghosting of the shell system, which we'll talk a little bit more about in a little bit. And so altogether, our system produces close to 400 cubic meters of space, occupiable space. That's after inflation, of course. And by optimizing the structure, optimizing the amount of mass that you carry with you, you wouldn't carry all the wet mass, like the water for shielding or for life support. All that gets placed into a separate shipment so that we can then optimize for only the mass required to maintain the structure. And that gives us something like a 47 metric ton mass habitat. And as you saw from the transportation capabilities, we can fit that within at least one or two of the vehicles that we looked at. Of course, dimensionally, we can play with that. We can play with the overall diameter, with the height. That's something that we've started to look at with different mission scenarios, depending on also the requirements that ESA has been fitting us. So then here's a breakdown of all the systems. And I think one of the interesting things here is you see that we've actually allocated a lot of working space. Working space here makes up almost 40 cubic meters of space. That's quite a bit. It's actually an entire floor. And that's because you know that when astronauts are building their careers up to work in an environment like this, that they're going to want to do a lot of research. And that's something that's very important for us. And so what we started with was we placed most of the EVA systems at the ground level, of course, because you want to interface with airlocks, with EVA tunnels, and also with vehicles at the ground floor. And then on the second floor, we placed all the working spaces. So directly coming out of an EVA, you can go into a workspace. Living spaces are on the third floor. And then on the fourth floor, we placed hydroponic systems for food growth, but also for biophilic effects and research. Here's, these drawings look better on paper, but just to give you a kind of quick overview. So on the left, you see the ground floor, and you can see that we're looking at how the airlock adapters connect to the tunnels, and then how the rack systems to support different EVA activities would be placed along the structure. And a big part of that is also defining the geometry. And so we look very closely at dimensional constraints for creating the geometry, the form. And then on the right, you see the second floor with all the rack systems displaced. And on the left here, you have the third floor, which is the crew quarters. And we imagine that the crew quarters would also have additional shielding. And so in the pocket of these crew systems, you would have about 100 to 200 millimeters of volume for water. So you can jacket the living quarters for sleeping quarters with additional radiation protection. And then on the right, you see the top floor where we have the hydroponic systems. This is the system broken apart. You can see that we started to look at how the shell is discretized into several panels. And the reason for that is because we're also taking on complex geometry, in which I'll talk about a little bit more. But the need to discretize is to find a way to stitch the different shell configurations together, since we're not working with only single curved geometry for the base form, but only after it's been optimized. And here's a depiction of all the geometry drawings to help define the form. So to talk about the shell a little bit more, our engineering group has been doing some finite element analysis, looking at directional stresses, both horizontal and vertical, or X and Y stresses. And what we've done is we've taken the edge condition as an attachment point, so that becomes the support link to the rigid shell, and then pressurizing it to 1 atmosphere, and looking at the variable conditions that the inflated state would have to undertake. And this has been really helpful in articulating the form and optimizing the shaping of it. But we've also done that with the rigid shell, where on the left we have an arc and a straight line to make up that entire habitat taper vertically. But what we've seen is that by introducing continuous curvature on the right, you can actually reduce the bending moments by more than half. And that's just to say that geometry has a big role to play in how structures can be optimized. And for this, we're using, of course, a lot of the software in-house, like SAP 2000. So here's a depiction of the habitat, much closer. So you see on the left is an interface with the shell adapter. And the way that we've been studying this is by looking at weaving conditions. So we've studied various weaving techniques, looking at some of the patents that NASA has already been developing for integrating rigid shells. And of course, there's a mass penalty for integrating rigid structures into an inflatable shell. But the key here is looking at how to tie the Vectran strands, which is a material of choice in this case. And we've looked at not just the connections at the airlock, but also connections to the frame and connections to the top, the bulkhead. And what we've studied here is we've studied that there's different configurations which work best in different scenarios. And so the only way to achieve this is by applying almost like an edge condition. So there's a boundary condition where you go from being an equatorial Vectran weave, which is a term we coined, to being a polar Vectran weave, where the density of the weaving connections actually get closer and closer as they come towards the bulkhead. And because of that, we have to space the Vectran strands very differently. And we've looked at also the kinds of Vectran types that we would use. So in this case, we're looking at a thickness of about 30 millimeters for the Vectran. Again, the drawings look better in paper, but here's a drawing of the different sections as you move up the column, just to have a better understanding of how we set the working points and how we're starting to define the structural interfaces with the floor system. And the floor system is also a unique challenge because you have to imagine that the floor system is deployed after the shell has been pressurized. And because of that, we need to optimize for mass and also for deployment. So we looked at one option where we have a folded configuration where concentric beams are actually making up the primary floor structure. But then we also looked at another one where we have a triangle which connects directly to the columns. But we realized that, in the study, we realized that actually it's the concentric structure which gives us the most opportunity for housing various equipment inside of the floor system, because the floor thickness has an assembly of about 400 millimeters. So we can take advantage of that. But the beams themselves are not that thick. I should clarify that. So we're using software called ETABS here to look at how to size the different members appropriately. And also looking at different materials. We've looked at steel, structural steel. We've looked at titanium. And we also looked at aluminum. Somebody said to me earlier that the cost sometimes outweighs the benefit. So titanium is something that, of course, has a much higher strength, but also the cost would have to be thought about if we were to use it. So aluminum seems to be the choice of material in this case. And you can see that the loading, it's hard to see actually the loading, but the loadings that we've taken into consideration are both the live and dead load. So looking at the rack systems as a whole and the capacity that each rack unit would be able to contain. And by placing all that load, summing it up, and making sure that it can function in both scenarios for both for live and dead load with maximum capacity. This is what that space looks like after it's been installed. And you can see that we've arrayed the entire rack system, and you can fit that rack system with any payload you want. And all circulation is centralized. And then this is the crew quarters. And you can see here that we've started to think about lighting very seriously. So to maintain circadian rhythms, we want to integrate various forms of lighting, but also various forms of entertainment. And we got a little bit playful with that. So if you can imagine a moon village to be established, some of the key factors here are also interfaces. And so interfaces have to be universal. And as you've seen in the drawings, we've taken that into consideration, but other elements such as horizontal habs, EVA units, or even tunnels need to interface with these habitats. And that's something that we have to consider. So moving forward, we want to talk about master planning, thinking about large-scale development, because after all, one habitat won't do it for all of us, but lunar activities that would need to take place and the kinds of systems that we need to consider would include human and robotic exploration science, of course. We need to make sure that we analyze the site, we characterize the materials, and that we identify where we're going. And then, of course, lunar resource development. We want to make sure that there is enough proof that we can actually process the material, we can make use of it, we can extract the water, that we can build. And then finally, the testing and deployment of surface systems like habitats, mobile equipment, and power stations. So this is all just a list of things that we've been planning for in our master planning thinking. And of course, when you think about the kinds of infrastructure that you would also build things for landing equipment like berms, because you want to shield your settlement from any projectiles from the plume. And so once we have additive manufacturing or in situ construction capabilities in place, then we can learn how to build berms and landing pads and roads so that we can mitigate the amount of dust that's being pushed around, because the dust has harmful effects on both equipment but also on humans. And to add additional shielding, we're also thinking about using additive manufacturing to shield our habitats. Limited shielding, of course, because you don't want to cover the entire habitat in regolith, but also this would be an early study of how to work with large-scale shell structures that could be built in place, in situ. So when you think about the first mission, we worked together with ESA to think about how we would actually get first habitat there. And the consensus is that the first launch, we would first deliver a lot of cargo. We would deliver mobility systems, and also maybe some proof of concept for ISRU, just so that we understand what's possible. In the second launch, we would start to send much bigger equipment, like the actual lander that would be capable of landing the habitat, and also a system that could actually take the habitat from the lander and place it on the ground. And so when we finally send the habitat, that wouldn't be until the third launch. And in the fourth launch, that's when the crew arrives. And so you can imagine that after 4 launches, you have a fully functioning habitat with crew, with the equipment, with proof of concept ISRU already conducted. And then you can start to sequence additional launches to send more habitats, more equipment, and more crew. And this is what the most recent study looks like, where on the left, we have the pre-in-place structures together with solar towers. And then as we develop the ecosystem of architecture, we see that there's a network being developed, a network that includes additional redundancy so that you don't have to do EVAs in order to get to an adjacent unit, but that there's a system of tunnels that get you from one unit to the next, and then also a network of roads to mitigate the dust dispersion. And then once we have these ready-made structures in place and we have a strong ecosystem and enough workforce, we can think about building ISRU structures like what you see on the right, a much more advanced version of what we imagine to be architecture. And of course, that needs a lot of power. And so you see that the power field on the bottom needs to go hand in hand with the settlement. So first, ready-made habitats, of course, landing pads, expansion of the first settlement, additional roads to connect you to deep to water ice deposits so that you can do some ISRU testing and development, and then power capabilities to increase the amount of energy that you can collect, and finally, advanced ISRU structures. All connected together by a network of roads. And of course, we didn't mention all the ISRU infrastructure that you would need, but in addition to some of the things that I mentioned, you can also think about granular mechanics as being a discipline that could be evolved on the lunar surface, civil engineering and construction, resource processing and production, of course. And these are different trades and disciplines that would be evolved only if we can get an ecosystem on the moon. And of course, a lot of people here would love to do science on the moon, I'm sure. And so that means that new modes of science could be conducted once we have a settlement on the moon. And the elements that would allow us to do that would be roads, landing pads, berms, habitats, and of course, shelters, since radiation is one of the biggest challenges to deal with. And so having ISRU capabilities means that you could shield yourself from galactic cosmic rays and solar particle events. And so we've looked at regolith based on literature review. We understand that regolith has a certain composition that has benefits. Of course, we know the cons, but compared to Portland cement, it's actually 5 times stronger in compression. And couple that together with 1,6G, and you can start to, your imagination starts to think about what's possible, what you can build with that. And so we studied that, and we took a look at using some of the digital technologies that we use for building structures and engineering to come up with concepts that really push the boundaries of what ISRE structures could be. But of course, you have to visit some precedent. And precedents like mud huts, for example, in Cameroon, these are really great precedents because they work in 2 ways. One is they use a very simple geometry, catenary curves, to create tall structures that are supported primarily by their geometry, not so much by their material mass. And then also looking at the articulation on the outside, you see that relief, which is actually a way to optimize the structure. So there's something that we can learn from, natively built structures, and we want to make sure that we look at all forms of architecture, not just the most advanced stuff. And then we also looked at various techniques for printing. For example, using concentrated solar energy or solar light, looking at gantry system 3D printing, like what I showed you before, and also contour crafting, some concepts that NASA has been working on. This is a US Army barracks, like I said before, that was built as a test, a pilot project to look at how you can very rapidly build protective shelters. And this was in collaboration with SOM. And I think one of the biggest challenges is not the speed of printing, but actually the equipment. The equipment tends to fail quite often. And so there's a lot to learn with that. And if you think about the abrasiveness of regolith, you're going to have to build robust equipment that can actually do the work. So a lot of people actually have to go and fix the equipment to make sure that it works. And so here's a concept that we put together, just one of many, but this concept takes some of those keynotes that we looked at from that case study, where we're looking at both the form, but we're also looking at the textural quality of the shell. And that allows us to optimize for mass, but also for the thickness required to do radiation shielding. And of course it's open, because this is not a habitable unit. You wouldn't go in here and pressurize it. You would only use this to protect your equipment, so you can do servicing of vehicles, servicing of experiments, and this would give you, it would actually extend the lifespan of any astronaut, because then you can provide the shielding required during their career. And so we used some finite element analysis to look at the form and the distribution of loads, and that's how we optimize the structure. And then here, what you see is you see a multi-objective optimization technique that we use, where we set the criteria. In this case, the criteria is structural performance, but also mass and volume. So you want to increase the occupiable volume, you want to decrease the mass, and you want to increase the structural performance or reduce the forces. And so we started off with what you see on the bottom, where you have a 3-cell configuration, but then after running the routine, the solver came up with a solution which actually looks very different. It's a 5-cell configuration, and you can see that the depth of the texture is actually much deeper. And that's that was interesting for us. So the computer is helping us solve for how to design these. Here's some 3D printed versions of that. And now if you can imagine, what would it look like to place this on the moon? This is how we imagine an ecosystem of ISRE structures taking place. Of course, a lot of the equipment that you see there, we didn't discuss, but we have to take some leaps here to start to imagine how you can place structures of this size on the moon. And so that's our moon village. And it's something that's continuing to grow. We're still working on this. If I was to tell you what the next steps were, the next steps are, we're going to definitely try to test some of these ideas and to start to think about prototyping. But we will have, for anyone who's interested, we will have an exhibit at the IAC coming to Washington, D.C. in October. So if you're interested, please come. We're going to have a lot of demonstrations. We're going to have some amazing experiences. We're going to have some VR headsets, and we look forward to seeing you there.
So we have time for some questions. I think my first question is, you might explain what IHD is.
What?
IHD is.
Oh, IAC. I'm sorry. It's the International Astronautical Congress. It's an event that comes, well, I think it's the first time it came to DC, but it happens once a year, and it's the biggest space event in the world, I think.
So we do have time for some questions. We have a procedure, raise your hand. There are 3 microphones, red, blue, black, and we'll go in that order. When the microphone comes to you, please stand up, tell us your name, tell us if you're a member, and ask a question. Save speeches and illuminating observations for the social hour, and you'll have lots of time for that. So we have a question in the front row here. The blue microphone. Keep your hand up long enough for the microphone runners to see you.
The what? Oh.
Please stand up, tell us your name, tell us if you're a member.
Dave Lonsfeld, not a member. 2 brief questions. Astronaut Congress costs about $1,000, doesn't it, to go to it? There's no way to see it, except on the Friday public day, I guess. Is that right? That's number 1. And number 2, your printed concrete buildings, are they do you use ductile for the concrete, or are the concrete integrally reinforced with, with fibers? Or how do you reinforce those printed, 3D printed concrete buildings there? Thank you.
Yeah. So a lot of the structures that you see there, they wouldn't be pressurized. The ISRU versions wouldn't be pressurized, which means they don't need too much reinforcement and tension, but they work great in compression. And so we're looking at two ways. One is sintering, where you actually use microwaves to sinter the material together, and because there's a lot of glass in the regolith, you can use that as an admixture, or we bring chemicals with us that we can introduce into the mixture.
Black microphone, don't carry on a dialogue, because this is being recorded and nobody can hear you.
Hi, I'm Christopher Knudsen. Great presentation tonight. Thanks for coming. I'm not a member yet of PSW, but interested in joining. My question for you is, with the regolith, it's obviously a very difficult material to work with. How are you able to, I guess, conduct experiments here on Earth without having a supply of that to work with? Thank you.
Yeah, that's a great question. So we do know that NASA JSC has been putting together a lot of simulant. It would be amazing for us to get a hold of some simulant and then to actually, work with it. We have, of course, we have 3D printing equipment already functioning for various applications that we see on Earth, especially with like the U.S. Army core experiment. So it would be excellent to try and, work with that. We are looking for those opportunities. Yeah.
Red microphone.
Hi, Carl Merrill, I'm a member. I always thought that one of the major problems, and you had one slide which mentioned it, was the problem of micrometeors and radiation. And in fact, the early work that I saw, people talked about burrowing under the soil to build the buildings. So the question I have is, what kind of data do you have on the rate of micrometeor hits? I mean, here on the Earth, we don't worry that much because we have an atmosphere. Here, you don't. And the other question is, what's the strength of the radiation and how much? And do these buildings you project really protect against that?
Yeah, that's a great question. So the habitats, the way that we've designed them, and of course a lot of the feedback that we're getting from our partners, is that they're not permanent settlements, obviously. They would only prolong the mission duration. As long as they meet the NASA standards for radiation, they can be used for up to 500-day missions, for example. But the only way that you can increase the radiation protection is by introducing things like boron-heavy materials or materials with a lot of hydrogen. So that's why we're jacketing the enclosure with water from the inside. Makes a lot of sense. But we imagine that the water wouldn't be shipped with the habitat. You would have to find ways of extracting the water in situ so that you can then take advantage of that. And then the ISRU structure would actually be, radiation proof. You would have enough thickness to really provide that kind of radiation, but those wouldn't be closed structures. They would only be for working. A lot of work would be done on the moon. And so we imagine that those structures would actually serve a big purpose, even though they're not pressurized.
And the micrometeorite?
And micrometeorites, we don't know the rate of micrometeorites impact, but it's something that we should definitely study. Yeah.
Blue microphone.
Hi, my name's Eric Kane. I'm a member. And it was a very impressive presentation, and clearly you've put a lot of time and effort and money, presumably, in order to do all of this. So I'm wondering, first of all, and maybe I missed it at the beginning, who is paying for all of this? And is there a plan to actually put this into practice to some extent, or is this purely a theoretical study?
Yeah, so I think what's interesting about the partnership is that everybody is funding it from their own side. So everybody is actually contributing, We're contributing, ESA's contributing, MIT's contributing. There's no exchange of funds happening. But the plan to apply this, we're still in discussions about that, and there's not much I can say about that, but except that we are seriously thinking about testing some of these concepts. And that's why I invite you guys to come to IAC, where you might see some of that taking place.
So we'll go red and then blue and then black.
Hi, Mayumi Okada, and I am a member. So how many people fit inside one of those units? And once you deliver all the stuff, will there be things coming back? And would we bring the regolith back with us to add to uses in the United States, well, uses in the world.
Yeah. So bringing things back from the moon doesn't make sense. It's so expensive. Not even water. I mean, anything you can find on the moon, I don't think it would make sense. It would be cost prohibitive to bring things back. But the habitats, they're designed to fit anywhere between 4 to 6 people at their current scales. And that's because they fit within the payload limitations, which I described earlier for the Falcon Heavy, the Blue Origin, and the BFR.
Blue microphone.
Kristen Ferry, and I am a member. With volume as well as weight being such a premium, why are the ceilings so high? Why do you have so much space there that seems initially as counterintuitive there?
Yeah, that's a good question. So in our designs, we looked very closely at the ISS modules. They're very small, but you're also, you're not bound to the ground. There's no up or down. But under 16G, you still do have a grounding. So you're going to have to stand on something. But then because of 16G, you also have a much higher reach, which means that in terms of like height, your reach is increased quite dramatically. You can imagine just jumping up like you normally do on the ground here and actually going much higher than you normally do. So we wanted to increase the volume, but of course also for air movement so that we can circulate air, for dispersing light, and for creating a habitable space that increases the human experience.
Black microphone somewhere.
Hi, my name is Nick Gorgone. I'm a member. My main question is, with such stringent requirements on what needs to be done, it's far more than anything in a regular building, right? And the geometric requirements, how much room is left for interpretation and architectural design, as it would be in some of the buildings that you showed before, Sagrada Familia, Guggenheim, amazing artistic pieces of work. Could you talk a little bit about that?
Yeah. Yeah, it's interesting. From the exterior perspective, I think, because a lot of architects design things from, looking at it from a distance. It's almost like objectified. Architecture is in some ways objectified, where in other cases, like if you look at cathedrals, it's really about the inside, the experience. In our case, it's very much about the inside experience. And it goes to the question that she asked, why we designed the floor to ceiling spaces so high. It's because we want to try and increase that quality, I guess. But also optimizing the functionality of every astronaut, since you want to increase performance. Like there's benefits to increase space, to increase lighting, to increase visibility. And so by doing that, you optimize performance in the long run.
Red microphone. Please stand up. Tell us your name.
Yeah. Hi, name is Larry Chen. I am not a part of the Philosophical Society, unfortunately, but I'd like to join. I had a quick question about sending a person there. I know that based on the fact that we already, have people living on the International Space Station for long periods of time, how would that be different, or would it be similar with a person living on the moon in terms of length as to how long they would be able to stay and effects on the body?
Good question.
Yeah, that's a really good question. The standards for absorbing radiation have already been set. And I know that they're much higher than when you work in a nuclear facility, for example. But I would imagine that they would make an exception for lunar missions. I mean, I don't know, I'm just speculating, but you would have to increase that threshold. And we don't understand the repercussions or the impacts on biology until we've actually tested that. I can only speculate, really, on how it would impact, human well-being. But we are designing for increasing, the well-being with a lot of the features that you see. But when it comes to radiation, that's something that it's just way outside of my understanding.
No.
Oh, yeah. And also to think about other kinds of human effects. If you think about gravity, reduced gravity, one of the key functions about a vertical configuration is that you induce movement. And because you induce movement, you force the occupants to use their body quite a bit. And that hopefully has some added benefits to it.
Is there any research on whether or not 1/6 gravity will prevent some of the ill effects of zero-G that they observe in people who've been on the ISS for a long time?
I don't know. That's a good question. We would have to look into that.
Okay, I think we are at the blue mic, then the red mic.
Hi, my name's Tal. I was wondering, when you're considering the materials that you use to produce these architecture, do you worry about biological organisms that we might inadvertently bring up into an environment that could cause structural degradation of the integrity over time?
You mean organisms on the moon?
Yeah, like when you're carrying materials, like, do you worry about bacterias or any?
I think she means the ones that you're going to bring there.
Oh, yeah. Well, I don't know if bacteria could actually survive on the moon, but that's a good question. I don't know the answer to that one. I'm sorry.
Let me do the online, and then you can go, Brett.
So our online questions, can you guys hear me? Yeah. Our online questions tonight are kind of related, and it has to do with the harsh lunar environment. The first question is, what considerations have been made to deal with the massive temperature differentials between day and night on the moon? And also, have you considered building inside lunar lava tubes to insulate against the harsh lunar environment?
What was the first part?
The first question was, what considerations have been made to deal with the massive temperature differentials between day and night on the moon? And also, building inside lunar lava tubes to insulate against the harsh lunar environment.
Yes. So when you look at the shell technology, most of that thickness, which is roughly about 300 millimeters, a big portion of that is only insulation. So that insulation actually keeps the extreme temperatures from penetrating the module. But also, we're occupying some of the highest points where you have near continuous sunlight. And so you're almost like at the threshold of deep space and daylight, which hopefully we can make use of by surrounding our structures with regolith and absorbing that energy and making it usable. So that's one technique. And of course, we would also be insulating our structures by building with regolith around them. And the second question, can you repeat the second question?
The lava tubes.
Yes, and the second question, so that has been brought up actually, but when you think about the kind of infrastructure that you need to build underground and the kinds of spaces that people would be inhabiting, it would be, in our opinion at least, or in this study, it was too detrimental to the human experience for us to actually consider that. So we tried to also use ready-made technologies, since what you see here is things that you can build today, things that you can actually test, things that have been tested by organizations like NASA. So we're really trying to make use of technologies that are working in place today.
Red microphone, Brett.
Brett Magram, member. This is more of a settlement question. I was curious, do these structures have foundations? And if so, could you give us some more details about the foundations? And if they don't have foundations and they're sitting just on the soil, what prevents, like the online question, thermal differentials from causing differential settlement or other sort of tipping the structure over time?
Yeah, that's a great question. So in all of the studies that we've done from the literature review, we saw that the soil samples from the Apollo missions, none of them ever actually went as far as hitting bedrock. They're all soil samples. So it's only like the top layer of the regolith. But in order for you to build a foundation, you would need to microwave to a certain depth. And in our studies, for the most part, we've looked at microwaving to a depth of 1 meter, which has been done in other studies. So if we were to build a foundation, you would first need the equipment to do the microwave sintering before you emplace a structure. But it wouldn't be fastened to the ground. The structures would actually just sit on top. They wouldn't be permanently fastened. Yeah.
I'm going to do the blue mic and then the red mic, and if somebody can get a mic to Tim, and then a black mic, and then Tim. Okay, so blue, and then red, and then black, and then Tim. I don't know.
Bob Hershey, I'm a member. What do you do about variations of properties of the regolith, such as the strength of the material?
Yeah, that's great. That's a great question. That's why you need to have processing units, so that if you can characterize a location on the moon where it has certain characteristics for increased strength, or you want to extract certain minerals, then you have to make sure that you collect that material, you process it, and it becomes a standard grade, if you will. And then you can use it for building, much like what we do on Earth.
So it's the red guy who hasn't paid his dues back there.
Will Angel, I am now a member.
Oh, you have? I take it back.
Thank you. You mentioned that there would be tunnels dug underneath the roads to connect habitats. How would those tunnels be dug? And could that same technology be used to build underground structures?
I'm sorry, maybe I misinterpreted that part, but did you say tunnels? I don't think I mentioned tunnels. I did mention a network of roads, but not tunnels. The tunnels that connect the habitats are actually above ground. Yes. And that's there for redundancy, so that when you think about moving between adjacent structures, you don't have to actually go outside into the lunar environment. Yeah.
Black microphone.
Hi, Cassie Taylor, not a member. Do you know, are there other groups internationally working on similar projects, or is it just this group of your 3-4 organizations?
Yeah, no, there's the NASA Centennial Challenge, for example, where they're focused on additive manufacturing. But I do know that there's interest, for sure, from architects around the world to work on these kinds of projects. Another one that comes to mind actually predates what we did. Foster and Partners did a project. They were also focused on ISRU construction. But there's definitely interest, and it's increasing, since you see that there's a lot of attention being paid to going to space and future space exploration.
Let me sneak a question in there. Have you spoken to the SpaceX people, and have they got planning like this for their planned colonies on Mars?
I know that during their presentations, I've seen some images that SpaceX has presented that talks about settlement on Mars, but to what extent they actually investigate those concepts, I'm not sure. And no, I don't have any contacts with SpaceX.
Okay. Nobody does.
I'm Timothy Thomas. I'm a member. I notice you don't have any defensive facilities. Are you foolishly assuming that humans on the moon will be peaceful?
We're hoping that an endeavor like this would unite us. So, yes.
We'll take an online question, then we'll go back to Red over here.
This question was actually from me, Larry, Ann McQueen, member, and it bounces off of Larry's question as well. I was just wondering if you guys had done any feasibility studies for your architecture and design here to see if it would be compatible with a base on Mars or an asteroid or something like that. Have you guys gone beyond the moon as far as your technology and your architecture goes, your design?
No, we've only studied the moon. Sorry.
Linda Voss, I'm a guest. The two major problems with spaceflight that we're working on right now are the loss of bone calcium and, of course, the radiation problem. So I'm really interested that you're using water as your shielding, and also I'm assuming that you're not letting it freeze but keeping it liquid. Are you doing anything to deal with the calcium loss in particular? I know at 1/6 gravity you'd still be dealing with a lot of that loss. There are actually a lot of studies done about the effects of microgravity or lack of gravity on things like the shape of the eye and problems with vision that particularly the male astronauts have from the space station. So there are a lot of studies based on the space station about the physiological changes. The twin study was a big one. And so the main question is just, are you dealing with the bone loss of calcium? Do you have any plans for physical facilities or the kinds of things that would help keep your astronauts from turning into jellyfish?
Yeah, I think I mentioned it before, but a big part of the strategy is to induce movement. And so I know I keep saying centralized movement, but we also have concepts which I didn't really talk about today, where movement is actually taking place around the perimeter, which allows for additional movement. So we're really trying to come up with an architecture which forces people to move and to use their muscles and their body. And that's been one of the biggest drivers. But all we can do as designers of the architecture is really just design and architecture which considers these kinds of limitations, but we can't think, we don't have a direct impact on, for example, like the kinds of like medical equipment that would be required to maintain human health. These are all payloads that we would have to, of course, have some input on, but we integrate that information. So the closer we get to people who know about this, like you, the better we can integrate our systems holistically. And those are conversations that we're willing to have with anyone. But we do have some people from ESA working on ECLSS systems, so we've been thinking about it.
Is the black microphone out there somewhere? If not, the last question would be the red microphone here.
Mike Moore, I'm a member. I worry a lot about contamination control. The Apollo guys got spacesuits that were starting to quit working because of the contamination from the dust and regolith. I didn't actually see anything on that floor. Maybe you don't have that detail yet, but is there a process or a concept in here?
Yeah. So none of that unsuiting takes place inside of the habitat. That actually takes place in an adjacent structure, which would be considered the airlock tunnel. So I mentioned in some of the visuals where we have airlock tunnels that actually connect to the habitat through the adapter, but the dust off, all that takes place outside in a separate structure, which we're not designing. We're not really designing those things, but of course you would have to interface with those systems. But we're not bringing any of that regolith into our designs.
Well, thank you very much. I'll see you on the moon.
Yes, thank you.
So before you go, we have a small token of appreciation for your coming here and speaking to us. It's a framed copy of the announcement of your lecture, signed by all the members of the General Committee on behalf of you, the members of PSW. And we also have a signed copy of the Bulletin of the Philosophical Society of Washington, Volume 1, which tells you why it was founded, who the original members were, what the bylaws were, and why it was called philosophical.
Thank you.
Even though it was all about science.
Thank you so much.
Thank you very much.
Thank you, Larry.
You'll be able to ask questions in the social hour, but give them a couple of minutes. So before we go, we have a few closing announcements. PSW depends on members and sponsors and volunteers. So if you are a member, please note the 2019-2020, believe it or not, notices have been sent. If you've not yet paid your dues, please pay. And please consider making an additional donation, sponsoring a lecture or a lecture series, and volunteering to help carry out the Society's activities. If you're not a member, please consider joining. It's easy enough to do. You just go to the home page and click on the join button. Wow. And that will pull up this page, which has a link here that pulls up the application for membership page, which, you know, I should take my own advice and use the confidence monitor over here. And you fill that out, including all of the asterisk fields, and press the little submit button, and you'll be asked for money. You can pay with a credit card. You don't have to pay with PayPal. Please make the payment, and your application will be considered. The standards for admission to PSW are incredibly high. You must have a genuine interest in science. And as long as you have a genuine interest in science, you will be welcomed to the society. So if you're not a member, please join. We're looking forward to establishing a branch on the moon. Upcoming lectures. Our next lecture will be on immortal spacecraft, the rise of in-space servicing, assembly, and manufacturing. The speaker will be Benjamin Reed, who is the Deputy Director of the Satellite Servicing Projects Division at NASA Goddard Space Flight Center. It might be a good follow-on to this lecture. After that, on October 18th, at the 2414th meeting, we have a lecture by Neil Deverov, who is a professor of chemistry and biochemistry and of bioengineering at the University of California, San Diego, and he will be speaking on like life, bottom-up synthetic biology. On November 1st, the 2415th meeting will be a lecture by George Bricker, who is the principal investigator on the Transiting Exoplanet Survey Satellite Mission, fondly known as TESS. And believe it or not, he'll be talking about TESS and the exoplanets that TESS has so far discovered. He is the director of the CCD lab as well as the TESS PI, and he's at MIT Kavli Institute for Astrophysics and Space Research. On November 15th, we'll have a talk by Dean Romich, who is Distinguished Professor of Oceanography at the Scripps Institute of Oceanography at the University of California, San Diego, in beautiful La Jolla. He's going to be talking about global autonomous ocean sensor flotillas, especially Argo, which is an integrated observation system of autonomous sensors that is floating in the Pacific. It's about 3,000 sensors, and they float with the currents, and then they go down to a depth periodically. And on the way up, they make measurements of temperature and salinity and velocity of the current. And when they get to the top, they report this all. And they've been doing this for quite some time, and he has quite an incredible database that gives us a very detailed look at the oceans in a way that we've never had before. On December 6th, we have a talk by Harold Hess, who's the group leader at HHMI Genelia, on the brain in super resolution 3D large volume molecular mapping of brain circuits. It should prove to be a very interesting talk. Harold is a good friend of Eric Betzig, who won the Nobel Prize not too long ago for developing microscopy methods that allow you to go beyond the supposed resolution limit of light microscopy. On the 10th, we don't know who we're going to have, but we'll have somebody. We have moved this year's President's Lecture to a little later because we have a talk by the inventor of cryo-electron microscopy, who also won a Nobel Prize not too long ago. And that will be our President's Dinner. And I'll tell you about that next time. And then finally, on January 24th, we have a talk on Venus by Ellen Stofan, who is the Adrian Mars Director of Smithsonian's National Air and Space Museum. The schedule is, at this moment, complete through March and will be posted in the not-distant future for the spring lectures. I should tell you that just today, the person who put together the consortium that imaged the black hole not too long ago is going to be speaking in May. So, see, with that, please thank tonight's crew. And please also join me in thanking the members of the General Committee who ensure that the Society is well run and solvent and do all the work required to hold the Society's meetings and present these lectures. And believe it or not, they don't get paid. I will now accept a motion from a member to adjourn the forgot to mention there's a social hour. As soon as we adjourn, it ends at 10:30 promptly. I will now accept a motion for adjournment of the 2412th meeting of the Society to that social hour. Bob, Mike, all in favor? Aye. All opposed? We are adjourned to the social hour. Thank you all for coming.